All right, guess what? It's our third lesson on 13.5. Are you sick of that yet? Well, actually, we've kind of hinted at some of this stuff before. Just now we're going to really focus on some of the notation and some of this terminology. Definitely the term conditional probability, like really the word given. That's kind of the new thing on this part. And really, how do you prove that something is independent? We've talked about, well, if it's independent, then you do such and such, or this is when you can multiply. But if you're trying to determine if something is really independent, you know all the probabilities. But if you're trying to show, this is the term I can remember, show with a calculation that these events are independent. You're going to want to be able to do that on the test. So let's get to it. All right, so this is the new notation. It's this vertical slash. This is the probability of B given A. So that's how you read this. The probability of B slash A is the probability that the event B occurs given that we already know that event A has occurred. And it's called conditional probability, as the occurrence of the second event is conditional, like it rests upon the knowledge that we know that A has already occurred. So part of this, you don't really have to compute the probability of A happening. It's just that we're within the new sample space of A happening. Now what's the probability that B has also happened? Which is exactly what this appears to show. Probability of B given A is out of new sample space A, because we know that's happened. We're only talking about these possibilities. What's the probability that B has also happened? So what's the probability of B and A happening out of all the times when A happens? Or if you rearrange that a little bit, this is just taking this equation and multiplying both sides of it by A, then it looks like this. That numerator over there just took A and multiplied the other side. The probability of B and A happening, this is this is nice. This is a more generic rule for how do you find the intersection of two events? How do you find the probability of B and A? It's the probability of A times the probability of B given that A has happened. This may not make as much sense right now, but this is really handy for proving why. Remember that thing I was saying a second ago? If you had to prove why things are independent, that would be really good in the future when we have to do that. We'll come back to that. Anyway, this is always true. This is true regardless of independence. But if they are independent, there's a special thing that happens with that. So we will see that in a minute. All right, there's a lot of words on this panel. Sorry, I didn't know where to divide this when I went to make this into a video. I wanted to keep it all kind of accessible at the same time. So sorry for that. You should recall from the first probability lesson that we dealt with sample space as the set of all possible outcomes. Conditional probability is when the original sample space of the experiment is now just kind of that thing that's after the slash. It's just, like we were talking about on the last page there, is B given A, so it's just the A part. So this is all the kids who are speaking Spanish, and this is the number of kids who speak Mandarin. So there's 150, 161 kids who speak Spanish. There's over 200 that speak Mandarin. There's 37 that speak both, and there's 27 that speak neither. That's what all those things stand for. These little separate numbers are separate groups where there's no overlap. 124 have Spanish only, no Mandarin. 178 are Mandarin only, no Spanish, as you know. Okay, so if we're trying to find the probability that randomly selected students speak Spanish, it's just 163 out of the total. I didn't know I found the total. The total is out of 366, which is like 44.5%. If we add the condition, if we say, what's the probability that this person speaks Spanish given that they already speak Mandarin? So among the Mandarin speakers, what's the probability, if I'm at the Mandarin speaking party, now what's the probability I find a Spanish speaker? That's different than just looking for Spanish speaking people in general. Just looking for Spanish people in the party of 366 people. What if I'm at the party of just 215? Well, that probability is different. It's only 37 out of those 215, and it's a totally different probability. You can read that again if you want to see why that's different. That's not a bad idea. So if we limit it to just the Mandarin speakers and now say, okay, what's the chance of picking a Spanish-speaking person? It's totally different. Notice if we had said, what's the other probability? Okay, so we're talking about, this was Spanish given Mandarin. That's not the same as Mandarin given Spanish. This rarely happens. So if we did that the other way, what's the probability you speak Mandarin given that you speak Spanish? Okay, so that's a different question. Now we're going to the Spanish-speaking party, and we're saying, how many of you guys speak Mandarin? That's 37 out of 161. See, different party. This was out of, whoa, why did that move? This is out of 161. This 37 makes 23%, but out of the 215, it makes only 17%. So they're totally different. So when you read this, here's another hint. When you're saying probability of B given A or the probability of A given B, when you're thinking, okay, how do I change this into a fraction? How do I actually compute this? One hint I think about is probability of B slash A. It's almost like if you were writing it, I kind of think of it this way. Probability of B given A, okay, where's my pointer? There it is. Probability of B given A, if you slant that a little bit, it almost looks like a fraction where it's B over A. That can help you remember that A goes on the bottom. On the top of this thing, though, it's always the both. It's always the both. On the last page, it didn't say both. On the last page, it said this fancy notation with the intersection, but it always means both. If we were going to do A given B, different fraction, probability of A given B, well, that just means you put the B on the bottom. Probability of B. That means over. It kind of makes me think of over B. It's not really, but it's going to help you get it right. So again, the numerator is still the both. Notice how the numerators of those two are the same. They're all 37, but it's out of a different total. It's out of the thing that we're given has happened. Okay, that's for Venn diagrams. They're not always Venn diagrams, but they're always that way with the given and the slash and the divided by and the denominator thing. Certain events are independent and thus are unaffected by the imposition of a condition. If you think about this, if we had independent events, remember how independent was defined as if one thing doesn't affect the other, then they are totally independent. So now if you think about this whole conditional thing, what that means is if they're independent, the condition shouldn't change the probability. It might change the numerator and the denominator, but the answer should still be the same percentage as when we started before we even took a condition. In other words, if we try to find the probability of B given A, the given A shouldn't affect the overall percentage. We should have the same percentage of B overall as we do percentage of B at the A party, because A doesn't affect B. So we should find the same proportion of B no matter where we look, whether it's in everybody or among people who speak A. All right. Events that are physically independent are also statistically independent. That's kind of a strange term, actually, but it's true, I guess. Physical independence is things like dice and coins and stuff. And so it's clearly we know that one does not affect the next. But who knows? We don't know enough about Mandarin speakers and Spanish speakers in different places and different communities. So maybe sometimes you'll find more Spanish speakers among the Mandarin community, and maybe some places you won't. So knowing whether or not that's dependent or independent is kind of crazy. Dice and coins and cards and stuff, that's, we can kind of tell empirically if that's going to be dependent or not. But here's a great way to test if it's independent. If you can figure out this probability, the probability of B amongst A, if that's the same as B overall, then A had nothing to do with it. Whether or not this slash A is here makes no difference. A does not influence B at all. Looking back to that one we talked about a second ago, remember if those are the same, this would be the same as the probability of B. So we might as well just write probability of B there. And of course, this is if independent. This is just about independence. If it turns out that the A and B is actually the multiplication of A and B, remember we had that as a rule before. If you knew they're independent, you can go ahead and multiply them. You can also use this to show, well, if you know the probability of A and B happening, and you know A and B separately, and if it turns out you can multiply them and you get the A and B, you've just showed that the B and that B given A are exactly the same. In other words, you've shown that they're independent. So these are great calculations for showing that they're independent. And yes, you're going to have to do that. All right, so we'll do that relatively soon. Okay, so here's a huge Venn diagram. It says, and I started pre-filling this out with the circles because, quite frankly, they're hard to draw. So I did this so we could fill this out together. It says there's 21 chemistry, 24 physics, 17 bio, and those are, of course, are the totals. There's 21 in chemistry, which includes, like if we call this top circle chemistry, this entire circle should add up to 21. This entire circle should add up to 24. This entire circle should add up to 17. And the total of everybody in the sample space, which might include people who are not in any one. So there might even be, we don't know this right away, but there might be some people that are actually in none of the classes. We got to keep a blank out here for that. The total of all this stuff should add to 58. Remember, there should be some overlap. Physics and chemistry could have some people in common. Bio and physics could have some people in common. So let's fill this out because we don't know what goes in all these little bubbles. Okay, 5 students take physics and chemistry. Well, physics and chemistry, that's kind of this football right here. I don't know how many are in all 3 and how many are in just the 2, so I'm going to wait on that. 4 students take chemistry and biology, similar problem. Let me wait for a second. 3 students take biology and physics. Oh, okay, here's the important part. 2 students take all 3. You really want to start in there because that's going to eat away at all these other intersections. Notice how the 2 is part of all these other footballs. All right, let's go back to this now. 5 take physics and chemistry. Physics and chemistry, this football or fish or whatever it is, this is supposed to be 5, so I know that's 3. You with me? I got that 3 from this 5. 5 are in here. 4 are in chemistry and bio. So this football has to be 4. Thank you very much. And 3 take biology and physics. So biology and physics, this is supposed to be 3. So there we go. Now I can fill out the rest of this. There's supposed to be 24 in physics total. 6 are kind of spoken for with the overlap with other classes. So there's 18 left. 21 take chem, while 7 are kind of already in here. So there's only 14 that are solely in chemistry. And bio has 17 total, so this must be 12. Now, every one of these single numbers is totally a separate group of people that take, just those particular classes. I can add all that up and figure out how many there are, and I can figure out how many are in the none category. That's a lot. This is 24, 26, 28, 32, 42, 52. I get 6 on the outside of everything. Okay, so I recopied the problem here so I can see it on the same page as where I'm doing the actual questions. Find the probability that a student takes no science. Okay, so any randomly selected student, that's out of the whole group of 58. What's the probability that they take no science? Oh, I already figured that out. It's 6. See, once you have all this sample space stuff figured out and who goes where, life is a lot simpler. Great. Find the probability that a student takes biology. Given that, denominator is no longer 58. They take physics. Okay, so given that physics means the denominator is the physics. Of this 24, so now focus your attention on the 24. What's the probability that if you're in there, you also take biology? Inside this, who takes biology? Those 3. That's kind of tricky. That's probability of bio given physics. So that's like bio and physics, which is the 3, divided by just physics, which is the 24. Find the probability they take physics. Given that, okay, given that means divided by bio. All right, bio is 17. Physics, given that they take bio, physics given that, okay, so of the 17, remember this is my new sample space. Of those 17, how are in physics? 3. Find the probability, so notice that. Biology given physics is 1 out of 8. Physics given biology, totally different. Find the probability they take chemistry. Given that, okay, it's very important. Do not take physics. So out of everybody who doesn't take physics, how many people don't take physics? Well, there's 24 in here. There's 58 total. So if 24 are taking physics, I could add these up. 12 plus 2 plus 14 plus 6. That's 20, 34. Or I could think 58 minus 24. Either way, I'm going to get 34 outside the physics circle. How many of those 34, so everybody outside physics, how many of those take chemistry? That would be outside of physics, who takes chemistry? This 14 and this 2. I see 16. Okay. Can I finish this in another minute? Probably not. Actually, it makes me want to stop right now. Okay, I will stop here and then we'll do a part 2 in a second.